Question 4. So, Dijkstra's algorithm finds the shortest path between a given start node and every other node in a weighted graph. Describe two applications of Dijkstra's algorithm. Guys, this is the easiest thing imaginable, right? What things need a short path? You could literally do anything, right? So the example I'm going to think of is, let's say you're sightseeing around Rome, for example. You're sightseeing around Rome. What do I want to do? Well, I'm at the Colosseum and I want to get to the Spanish Steps. What is the quickest way for me to get there? Well, I could go via the Trevi Fountain and get there, or I could go via the Pantheon and go this way, or I could go, then there's another thing in the way maybe, and I could go via somewhere over here, right? This is simply enough how to get from one place to another with shortest distances. This is one example where I just want to get from one place to another quickly. That's an example, and this would be perfectly fine. Like, what do the edges represent? Well, edges represent the distances between locations, right? Distances between locations, and you could definitely use Dijkstra's to figure out a nice quick way to get to the Spanish Steps via some other attractions. So that's step 1. Oh, what other things need a quick route? Well, if I'm sending someone a message, I want it to go directly to them and not via some routers, some random routers on the other way, right? So you could have sending packets across the network, right? If I'm sending anyone a message, you're going to send it in the form of packets via some routers across some networks, right? So here's my house, here's my friend's house. I want to kind of go via some routers on the way, right? But is it quicker to kind of bounce around like this? Or is it quicker to go directly this way? Or is it quicker to go there, and then here, right? Anything that needs the shortest path you can do. Here's another one, sending packets across the network. What are the edges? Well, if I want to find the shortest time, maybe the best one now, so it might be time taken for packets to travel between routers or whatever. And then you'd want to reduce that as much as possible, and that's it, right? So shortest time between house to house, or shortest distance between place and place. Anything like this would work. Anything else that's reasonable would work. I've got another example here that involves project milestones, right? And how do I get this milestone? Well, I could do this process, or I could actually do it, but I could solve it a different method that needs less effort, and then less time to do, and then maybe you could Dijkstra's that if you put your milestones as a graph. Anything that's to do with reducing the amount of time or effort or distance needed to do something, you could definitely use Dijkstra's. And that's that. So we'll move on to the next question. Here we are. In the algorithm below, find the shortest distances from A to the other nodes. A tentative node distance from A to every other node is initially assigned. So this is classic Dijkstra's algorithm. It's what they're going to ask you to do. So note that they've given you Dijkstra's algorithm here, which is fantastic. Okay, this is how you would do it in algorithm, but often you can just use your knowledge with these because you can kind of tell it's Dijkstra's. So what is the first thing that happened? Well, we're starting at A. Right, what's the distance from A to A? 0. Have we figured out how to get any of the other nodes yet? No. So initially, we don't know the best way to get anywhere. So they're all infinity. We don't know the best way to get anywhere. So they're all infinity right now. Initially, that's what it is. In the second row, show the tentative distances after A and the next node have been visited. So let's do A. So you visit A when you've done every neighbor of A. So B is initially set to 10. Distance from A to C is 12. Distance from A to D is 6. Okay, and then you guys do it. So we haven't finished yet, but this is just for the time being. Okay. Now, well, what's the shortest place in the queue? Other than A, we've done A. A's been visited, so we're going to do all the neighbors from 6 now. So I've done here, here, and here. So I'm done with A. I'm now doing the next shortest distance. So we're now going to start going from D. So how do I get from D anywhere? Well, D back to A is irrelevant because we've done A. But D to C, well, we've got 6 plus 5. So actually, that's better than 12. And that becomes 11. Okay, where else can I go from D? Well, I can go to F. Well, that's 6 plus 12, which gives me 18. So I can update like this. And this is my answer. That's it. Because you visit something when you've completely done all of their neighbors. We completely did all of A, and then we did the next shortest node, which is D, and then we did all of D. And then that's it.